Hello, my name is Ahmed Ibrahim. I'm a PhD candidate at the Department of Civil Engineering at McGill University, and today I would like to share with you some of our work on the continuum-based modeling or the two-fluid modeling of soil-water mixtures, as well as some insights on internal erosion around leaking pipes. The points I want to touch on today are basically some background review on particulate flow modeling, especially in civil and geotechnical engineering, which is the rationale behind this work and the answer to the question, why do we need to resort to such complex analysis while having well-established conventional methods? Also some theoretical background and numerical implementation of the two-fluid model, and eventually I'd like to share with you some of the results on the model validation problems and simulation of internal erosion. So the interaction between water, soil, or rocks is fundamental to understanding and designing a wide range of engineering applications. It affects the state of stresses, deformation, and ultimately might govern the design process altogether. And we have quite well-established methods that are basically continuum-based methods to do that. For instance, in the case of earth dams, these methods allow us to calculate the seepage through the earth dams. It allows us to calculate the factors of safety against piping or blowout. It can also help us determine the slope stability and get the factors of safety we need. However, the shortage of these methods emerges when we have to either dive into the micro scale or deal with the dynamic case. For instance, although I can calculate the seepage, but if internal erosion happens, it doesn't really tell us much about how this happened or the progression of cracks that is happening in case of rain-induced landslides. It doesn't tell us much about what happens to the debris and the extent of the runout that will occur. An interesting case that we'll be focusing on here is the evolution of cavities around leaking pipes. What happens here is that the pressurized water fluidizes the soil particles and might lead to some cavities that can eventually lead to a sinkhole. For that, we need to account for the full dynamics of both phases, water and soil, and these dynamics need to be coupled together. And the key element to achieve this coupling is the particle-fluid interaction forces. So keep in mind, now we're not looking at soil as a continuum mass that is essentially larger than a representative volume element. Rather, we're diving into the micro scale where soils are individual particles that affect the surrounding fluid and vice versa. And accounting for these forces within the dynamics of both phases is the key to that coupling. So in that kind of simulation, what we do is basically we implement the governing equations for these separate particles along with fluid as well as the coupling forces and see what happens in our system. So to clarify a little bit, let me share with you some of our simulation results on coupled discrete element modeling with CFD for a granular column collapse. This problem is becoming more popular among researchers to characterize marine landslides. And in this problem, we have a granular column here, and it's submerged into water, that is the blue background, and the front wall is suddenly removed. So we can see that along with the expected granular collapse, we also account for the water movement around and it's creating the vortices and everything. Look at the pressure values for the simulation, we can see the evolution of the pressure field that actually displays quite interesting information about the negative pressure development due to the dilation here and the extra pressure that's happening in the toe. This provides us with very detailed information both spatially and temporally that might be critical to some cases of analysis. However, this is very computationally expensive. The setting that is quite smaller than your laptop screen, than if you have a small one. 1 second of simulation corresponds to more than 4 hours of runtime, which is not feasible to carry out analysis of realistic systems that can actually serve the design process or risk assessment. So now our question is, can we still do the same thing, that accounting for the micromechanics of the system, while working in a continuum-based environment that is mesh-based, where we can refine and make coarse meshes in some places and save some computational costs? And the answer to that is the two-fluid model, where the representation of the particulate system, that is particles and fluid, is comprised of interpenetrating continua, and this is separating the two phases and then doing volume average over the computational cells. And these two phases overlap and interact together according to the governing equations to create this interpenetrating continua that contains the information of the micromechanics of the system, but yet it has a continuum representation. And if we look at the governing equations presented by Anderson and Jackson back in 1967, we can see they consist of the volume average, momentum, and continuity equations, with the particle fluid interaction forces appearing in different sides on the right-hand side of the momentum equations. Such representation is analogous to two fluids interacting together, where the solid phase appears as a fluid with some sort of viscosity and density that affects its behavior. This model has been used quite extensively in chemical engineering in the context of fluidized beds and pneumatic conveyors. However, in civil engineering, we still need some validation to make sure the model is able to replicate the behavior of water and soil in terms of initial seepage and dynamic movement. For that, we set up a simple case of a constant head tank connected to a sand column, applying constant pressure at the bottom, and the seepage velocity can be measured by Darcy's law here. If we look at the simulation results for seepage velocity against the upstream pressure, we can see it agrees well with some results of the empirical formulas for permeability and hydraulic conductivity. Note that here we're not using any of the Darcy equations parameters, no hydraulic conductivity, no permeability, just performing the calculations on a very fundamental level, which is in a sense a numerical experiment for permeability. If we give a look at the pressure field, the pressure distribution along the sample, it is linear, which is expected when the sample is intact and the integrity of the sand is not compromised. And this shows the model's ability to predict the movement of sand in this limited case. However, we want to make things more interesting. What if we increase the upstream pressure to be the same as the total stress at the bottom of the sand? In this case, a hydraulic instability will occur. And that's exactly what we can see here, as opposed to the first case where seepage was occurring. Now the sand particles are being pushed upwards, and we can see that around the rough edges here, some dead zones are being generated. So the model can successfully predict the seepage velocity. It can also predict the transition between seepage and dynamic movement. That gives us some confidence to move on to more complex simulation. In this case, we need to see what happens around leaking pipes. So instead of having the water passing through the entire column, now we only have a slot or little fracture that water is permitted to pass through. So the experimental setup is a submerged sand bed with a slot opening at the bottom, and this slot opening has water injected through it, either at constant pressure or constant flow rate. And in this case, we're expecting increase in the pore water pressure in the vicinity of the injection, as well as some fluidization near the location of the slot. So we carried out the simulation of water being injected through the slot. representing the leaking of a pressurized pipes. And here in the upper figure, we can see the distribution of excess pore water pressure across the bed compared with the experimental values reported by Saidalani back in 2010. And it shows quite good agreement. That means the model was able to capture the changes in pore water pressure and subsequently the effector stresses across the bed. Also, if we give a look here in the bottom figure at the flow rate predicted from the model, it seems to agree well around the corners um, for these 2 points. However, this point is when the fluidization was initiated of the particles. So it might be a shortcome due to the experimental technique that was used for measurement or some inherent drawback in the two-fluid model that needs further testing to identify. In addition, we wanted to test the model's ability to simulate more violent flows at higher flow rates at the ejection point, and we carried out this simulation and it shows good agreement with the experimental photographs taken at the same time. However, there seems to be some numerical diffusion effects, which is quite expected for continuum modeling. So in conclusion, the model can be a computationally feasible alternative for particular flow problems in civil engineering. Our initial testing for the model shows its ability to capture different flow regimes and transitions, such as seepage and dynamic fluidization. The results align quite well with the theoretical values and experimental reported values. Of course, more testing and rigorous validation problems need to be carried out before building complete trust in the model's ability.